Hi guys, it's Daniel here, and today we're going to do USAMTS year 28, which is this year, round number 1, problem number 3. So the approval for discussion has just been sent about a week ago, I think. So there's no harm in discussing round 1 of the USAMTS this year, so why not do one of the problems? Thus, let's look at what this problem states. Find all positive integers n for which x power of n plus y power of n plus z power of n over 2 is a perfect square whenever x, y, and z are integers such that x plus y plus z equals 0. So the first thing we notice is that we want this expression to be a perfect square whenever for any x, y, and z such that x plus y plus z equals 0. So this means even if we plug in specific values of x, y, z, this result still has to be 0, which tells us the motivation. What if we just plug in specific values of x, y, and z? Maybe like small values or convenient values such that we can cancel out some possible values of n. Because, for example, if we have an expression that can never be perfect square when n is a multiple of 3, then we've dwindled the list down to n congruent to 1 mod 3 and congruent to 2 mod 3, or something like that. So let's think about what we can plug in to solve this problem. Well, of course, there's first the x, y, z equals 0, but that actually doesn't tell us much because then this expression also equals 0, which is a perfect square. So the next thing to do is probably to plug in x equals -2, y equals z equals 1, because these numbers seem small enough. And though y equals 1 means that two of the numbers we don't even have to worry about the power of n. So let's see what happens when we plug these in. We have 1 to n plus 1 to n, that's just 2, plus -2 to the n, all over 2, which gives 1 plus factor a 2 out, -1 times -2 to the n minus 1. And this is a perfect square, so n squared. So now what do we notice here? Well, if n minus 1 is even, so n minus 1 even, then that means this expression is positive, which means that this expression is negative. And then we notice that -2 to the power of n minus 1, it becomes really big, really fast. In fact, for n equals, let's say 3 already, then this expression is equal to 1 plus -1 times 4, which is equal to 1 minus 4, which is -3, which is negative. And the thing we know about square numbers is that they're always greater than or equal to 0. So this tells us that when n is greater than or equal to 3, and n minus 1 is even, the left-hand side is negative and the right-hand side has to be positive, so we get contradiction. This is a contradiction. Of course, we can also manually check n equals 1, because this only covers the cases when n is greater than or equal to 3, and when n equals 1, x power of 1 plus y power of 1 plus z power of 1 over 2 is equal to 0 by the condition itself. So n equals 1 actually works. N equals 1 is a solution. So now all we need to do is check n minus 1 is odd. So this is n minus 1 even. Now let's do n minus 1 odd. So now our previous method here won't work anymore, because when n minus 1 is odd, n is even, so that means everything in here will definitely be positive. So we can't do any of these negative versus positive bounding anymore. So we need to plug in something different. In this case, since we already tried -2, 1, and 1, why not try x equals 2, y equals z equals -1? Because -1 is still quite a small number, and we don't have to worry about taking to the power of some, making it getting bigger and bigger, and because now all the -1 to the power of n, -1 to the power of n on these two will just alternate between -1 and 1. So let's see what happens here. we get 2 to the power of n plus negative 1 to the power of n times 2 over 2, which is just equal to 2 to the n minus 1, plus negative 1 to the n. We know that n minus 1 is odd, so that means n is even, so that means this thing is just equal to 2 to the n minus 1 plus 1. And this equals n squared. So now we can rearrange this a little bit to get 2 to the n minus 1 is equal to n squared minus 1, which is just equal to n plus 1 times n minus 1. So now this is actually really useful because we see that n plus 1 and n minus 1 multiply together to be a power of 2, which means that n plus 1 and n minus 1 themselves also are powers of 2. So the question is, how can this be possible? Well, if n plus 1 and n minus 1 are both powers of 2, then that means that their GCD, let's see, if their GCD is, if we calculate their GCD, if n is odd, then that means, or n is even, that means their GCD, they're both odd numbers, they're consecutive odd numbers, so that means their GCD is 1, which means that since they're both powers of 2, their GCD is also a power of 2, and since it's 1, we must have that one of these numbers is 1 and the other number is 2 to the n minus 1. However, if this is the case, then we must have n equals 2, and so that means n minus 1 is 1, but then n plus 1 is 3, which is not a factor of 2, or not a factor of 2 to the n minus 1, which is a contradiction. If n is even, or sorry, if n is odd, then that means the GCD of two consecutive odd numbers is equal to 2. So n even equals bad. So if we consider n odd, big N odd, then the GCD is 2, which means that n minus 1 must equal to 2, and n plus 1 is 2 to the n minus 2. So n minus 1 equals 2, n plus 1 equals 2 to the power of n minus 2, and we know that n minus 1 is equal to 2, which means n equals 3, so n plus 1 equals 4, which means that 2 to the n minus 2 is equal to 4, so n equals 4, because 4 minus 2 is 2, and 2 to the power of 2 is 4. So now we get one possible solution of n, which is great. But we have to do one more thing, which is to check that this solution indeed actually gives a perfect square for any x, y, and z integers such that x plus y plus z equals 0. So the question is x to the 4 plus y to the 4 plus z to the 4 over 2 a perfect square? Is it square if x plus y plus z equals 0? Is this true? And in order to solve this, we can try to find some sort of algebraic identity that represents x to the power 4 plus y to the power 4 plus z to the power 4 over 2 in terms of perhaps x plus y plus z and some other smaller symmetric sums. Now, if we wanted to find x power 4, x power of some big number n plus y to the n plus z to the n over 2 in terms of smaller symmetric sums, then we can use Newton's sums method, which I believe I discussed in a previous video, which will be linked in this video in an annotation probably. But since x power 4 plus y to the power 4 z to the power 4 is small enough, we can probably just find the expression just by guessing and checking. Because if we wanted to find an x power 4 y to the power 4 z to the power 4 term, we'd probably want something like x plus y plus z times x cubed plus y cubed plus z cubed. This gets the x power 4 plus y to the power 4 plus z to the power 4. Of course, everything in here will be multiplied by 1/2. So this will get the x power 4 y to the power 4 z to the power 4 term, but it will also introduce some x cubed y cubed z, terms like that. So in order to get rid of them, we might multiply by, for example, xy plus yz plus zx times x squared plus y squared plus z squared, because if you think about it, the x squared multiplies with the xy to give x cubed y, the x squared multiplies by the xz to give x cubed z, and so on like that. But now we have an extra terms that look of the form x squared yz, y squared zx, and z squared xy. So in order to counterbalance that again, well, we can just actually add back whatever we subtracted from this, because x squared yz plus y squared zx plus z squared xy is actually just equal to xyz times x plus y plus z. So now everything in here is all balanced out, and we are only left with the x power 4 plus y power 4 plus z power 4 terms. Now, fortunately, we know that x plus y plus z equals 0, so that means all this is cancelled, all this is cancelled, and we're left with negative xy plus yz plus zx times x squared plus y squared plus z squared. Now, we can actually simplify x squared plus y squared plus z squared using x plus y plus z, because we know that x plus y plus z squared is equal to x squared plus y squared plus z squared plus 2xy plus yz plus zx. So if we bring this over on the other side, then since this is 0, what this value is right here is simply just xy plus yz plus zx. Don't forget the minus there, and the 1/2 in the front, times negative 2 xy plus yz plus zx by moving the 2xy, yz, zx on the other side. And now we can simplify this to get, well, the negative cancel out, the 2 and 1/2 cancel out. We're left with xy plus yz plus zx squared. And in fact, since xy, yz, zx are all positive, or not positive, all integers, then this thing is a perfect square. And since this thing equals x to the 4 plus y to the 4 plus z to the 4 over 2, we find that when n equals 4, this thing is indeed a perfect square always, whenever x plus y plus z equals 0, so that means n equals 4 is also a solution. So our two solutions are n equals 1 and n equals 4, and we are done.
So today we're going to be tackling a pretty hard math problem. It's going to have a very long proof, so I won't be able to explain everything in detail. Before you start the video, well, here's the math problem first.